Hello? Hello? Hello?
Yes, sir. Good morning, sir.
Hello?
Good morning, sir.
Hello, can you hear me?
Yes, sir. Yes, sir.
Hello?
Yes, sir.
Hello?
It's audible.
Okay, okay. Okay, yesterday I have to discuss some concept of structure of algebra, and at the same time definition of a group, and some other examples are also well defined here. Okay, and see some simple properties of simple groups. Now, one is the uniqueness of identity, and the second one is the uniqueness of universe, and the third one is the cancellation laws, and fourth one is the equations of the ax equals to b and y equal to b have unique solutions, and fifth one is the a inverse whole inverse equals to a, for all a belongs to g, and the sixth one is the AB whole inverse equals to D inverse and A inverse. Now, these are all simple properties of groups. Okay. Now, first of all, so you have to already yesterday we have to discuss what is the binary operation. Okay. Now, binary operation and also simple binary, ordinary binary compositions, and at the same time binary compositions. Now that is also did as binary operations, binary signs, and binary symbols. Now that is okay. Now here the ordinary operations are addition, subtraction, multiplication, division. These are all ordinary operations. Now here the additive inverse is subtraction. Now subtraction is also involved, that is the inverse of addition. Now that's why here the subtraction is also, that is not necessary, that is also involving in the addition binary operation is there. And at the same time, division is also one of the binary operation. Now that is also, that is an inverse of multiplication. So that is also well defined. Now here the particularly binary operations, here addition and multiplication. Now already we have to discuss the group and abelian group is there. Okay, and according to that here the special binary operations. See here, what is the special binary operations? Okay, now there is the special binary operations means addition modulo m. Say this is one. This operation is called addition modulo n. Okay, addition modulo n. Now here the any set is defined capital S equals to set of 0, 1, 2 and so on, n minus 1 being the elements. Because here n modulo means now here given the set is consisting 0 to n minus 1 elements given in the set. Here n being any positive integer is there. Okay. Here the particularly binary operation is defined addition modulo n on S. Now for any here A and B are any two elements given in the set. Now here addition modulo n defined in between A and B. Here A and B any two elements given in the set. Now that is 0, 1, 2 and so on, n minus 1. In particularly, now we are comparing with the alphabetical elements here, A and B both are elements given in the set. Now how to define the addition modulo n? Now A is A addition modulo n of B. Read as A addition modulo n of B. Now that is the meaning of n divides A plus B. Modulo means that is the divisible part. Here n divides A plus B. Okay. Now here n lies between 0 to n minus 1. Okay, that's enough. Here, what is the A addition modulo n of B? So when A plus B, when it is less than n, that value is A plus B. And A plus B is greater than or equal to n, that value is A plus B minus n. Now, here the simple definition is n divides A plus B, that is addition modulo n operation. Now, this is one of the special binary operation. Suppose, see students, here one of the example is here 2 addition modulo 4 of 3. Okay, just you have to see here 2 addition modulo 4 of 3. What is the value of this one? 4 divides 2 plus 3. 4 divides 2 plus 3 means now in generally 2 plus 3 is divided by 4. That is the meaning. 4 divides 2 plus 3 and it read as 2 plus 3 divided by 4. What is the value of 2 plus 3? 2 plus 3 is 5. 5 divided by 4 means what is the remainder? That is 1. Now that remainder is lies between 0 to 4. What is the modulo here? N value is 4. 4 minus 1 means 3. Therefore, modulo 4 elements of the set is 0, 1, 2, 3 is there. Okay. Now 4 is also substituting given in the set. 4 minus 1 is 3 is there. Now additional modulo 4 set of the elements is 0, 1, 2, 3. That's enough. Now here the remainder value is 1 is there. 1 is lies between 0 to 3 is there. Now that is also consisting of this additional modulo of 4. Now second example is 2 plus 3, 5. What is the meaning of 2 additional modulo 5 of 3? What is the result? Now that is simple. 2 plus 3 is 5. 5 divided by 5. 5 divided by 5. What is the remainder? 5 divided by 5 means remainder is 0. 5. Hello? 5 divided by 5 is 1 is there, but remainder is 0. Now that is the result. Because 5 additional modulo 5 of the set of elements is 0, 1, 2, 3, 4. Because now 5 n value is 5. 5 minus 1 is 4. Now what is the additional modulo 5 of the elements of the set? 0, 1, 2, 3, 4 is there. That's enough. Use the link to that. Okay. Okay, sure. Today I will send some PDFs, important PDFs in your WhatsApp group. Okay. Now that is each and every that also sharing share through WhatsApp is there. One group link is also just yesterday. I have to join there. Okay. Thank you. Next one. 2 plus 3 is 5. 5 divided by 5 means the remainder is 0. That's enough. And again, this is also addition modulo 3. What is the value of 2 addition modulo 3 of 1? It read as 2 addition modulo 3 of 1 means 2 plus 1 is 3. 3 divided by 3 means 1 time is also remainder is 0. Okay. So that is also 0 is also lies between 0, 1, 2 is there. Addition modulo 3 elements of the set is of 2 because 3 minus 2. Set of the elements is 0, 1, 2. Addition modulo 6 means 0, 1, 2, 3, 4. That is the addition modulo 6 of the elements. So 6 is divided by 2 plus 3. 6 divides 2 plus 3. 2 plus 3 means 5. 5 it is less than 6 is there. Therefore, that is the remainder. Okay, that is the answer. Therefore, finally, here the additional modulo n, the set of integers modulo n to form a group. Okay, because here n lies here giving the n modulo of the n of the elements of the set is 0, 1 to so on n minus 1. Now, addition modulo n, here a and b, the set of all integers with respect to addition modulo n to form a group, and it is also form an abelian group is also there. Okay, now that is also one of the theorem. Now that's why that is the structure of group is S under addition modulo n is a group, because each and every property must involve within the set. Suppose 1 plus 2, 3 is there, 2 plus 3, 5 is here. Okay, now closure condition is satisfied. Associativity is suppose you are taking any 3 elements. 1, 2, 3 is there. 1 addition modulo n of 2 of addition modulo n of 3. 1 plus 2 is 3. 3 plus 3 is 6 is there. 6 is also given in the set. So that's why associative law A plus of B plus C equal to A plus B of plus C under ordinary composition. With special binary composition means addition modulo n of B of addition modulo n of C, replacing addition by addition modulo n in associative law. We are getting the result is A addition modulo n of B addition modulo n of C. So associative law is also satisfied. Okay. And the third one is here, what is the additive identity? Ordinary composition addition, additive identity is 0. Now, in the same manner, addition modulo n, now here the additive identity is also 0. So 0 is also involving with each and every element. We are getting the element is same given in the set is there. Suppose we are taking 1 plus 0 is 1. Okay, 0 plus 1 is 1. Now 1 under additional modulo n of 0, 1. Okay, 0 additional modulo n of 1 is also 1. 1 is also given in the set. Therefore, 0 beats additive identity. That's why here additive identity is also involved within the set is there. Therefore, 0 is the identity. Now, each and every element must be an inverse is there. Okay. Now, there are because 0 beats identity element is there. Now, there are so many problems with respect to the addition modulo n of addition modulo n. Okay. Now, finally, here S under addition modulo n is a group because when the closure, associative, existence of identity, and existence of inverse. Inverse is also involved. Each and every element must have an inverse. Zero inverse is zero, but one inverse. Okay, one. How to get the one of the element inverse? One which we are getting the result is zero. When we are getting the result is zero, now that element is an inverse of one is there. Particularly here n addition modulo n is there. Okay, here n being the integer is there. Okay. Now, when the closure, associative, existence of identity, existence of inverse, then these are satisfied. Now, the given set with respect to the additional modulo n to form a group. Okay, that's enough. What is Bhargav? That's enough. Now, here that is the theorem. Additional modulo integers is denoted by Zn. N modulo integers is denoted by Zn because Z being the integer, N is the modulo of the part. Here N modulo of integers or integers modulo N. Now it is here the operation addition modulo N on Zn is called addition modulo N. Now what is the set of integers modulo N? What is the set of integers modulo N? Explain. Set of 0, 1, 2, so on, n minus 1. These are all elements of set of integers modulo n is there. In the same manner, multiplication modulo n is also well defined here. Okay. Now here, given the set is consisting a1, a2, and so on, an. Now this is the n modulo integers. Okay. Suppose we are taking this one. Okay, multiplication a1, a2, a3, so on, an being the elements. Okay, here that is also an being the elements. Okay, now here it is a1 and a1, a1, a2, a1, a3, a1, a4, and first row of the first element is combined with each and every column. a1 into a1 into a2, a1, a3, a1, a4. That is one a1, an. In the same manner, each and every element must coincide with the column of the element. Now we have to construct the composition table. Now, first of all, what is the composition table? First of all, you have to mention the set of the elements must be arranged in the columns and rows. Then we have to write we must write the automatically composition table. It has a formula here. Okay, that's it. Now suppose this is an into a1. an into a2 and an into a3. This is an into a4, so on, an into an. Now, this type of this concept is called composition table. Now, first of all, you have to write these elements must be arranged as the rows and columns. Now, with respect to the composition, multiplication is the composition. Now, we have to construct the given the elements must be arranged, fill in the entries. Okay, filling their entries under their conclusions. Okay. Now here example. Please just you have to listen carefully. Now this problem is very important. How to get this one? Okay. Now addition modulo 5. This is the special binary operation. Okay, just listen carefully here. Now the set of all integers with respect to the addition modulo 5 to form an abelian group. Now this question is given. Listen carefully. Now here just you have to observe this composition table. Please you must note down. Please everybody must note down how to given the question. Prove that Z5 under addition modulo 5 to form a group and also an abelian group. What are the set of integers with respect to the addition modulo 5 to form an abelian group. Okay, this is the question corresponding to this composition table. What is the composition table? Composition table means here first of all, so you have to mention what is that special binary operation, that is addition modulo 5. This is the special binary composition or special binary operation. Ordinary addition is given. That's why you have to mention the plus is there. Okay. Now, what is the Z5 set? Integers modulo 5 of the set is set of 0, 1, 2, 3, 4. Because n value is 5. Now, given in the set of integers modulo n up to n minus 1 elements. Here n value is 5, 5 minus 1 is 4. That's why Z5 set is 0, 1, 2, 3, 4. That is the integers modulo of 5. Set of 0, 1, 2, 3, 4. Those elements must be arranged as the columns and the rows. Okay. Now, just you have to see here, 0 plus 0 is 0. 0 plus 1 is 1 because now these values are less than 5. Already the above definition is there. See here. Suppose A plus B, ordinary addition. Okay, A plus B, suppose it is less than n, we are getting the value is A plus B. That is, in the same manner, just you have to observe here, 0 plus 0, because it is less than 5. Now we are getting the result is 0. This is A and this is B. 0 plus 0 is 0, but it is less than 5. Now, that is the remainder is also here, that is the result. Now, 0 plus 1 is 1. Okay, and 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4 is there. Okay, that's enough. And at the same time, 1 plus 0, 1. 1 plus 1 is 2. 1 plus 2. Okay, that is 3. And observe, 1 plus 3, 4. Now, plus means here additional modulo 5 is there. But it is there less than 5 of the result is there here. 1 plus 2, 3. 3 less than 5. So, automatically we must mention the result is here. 1 plus 3, 4. 1 plus 4, 5. Just you have to see here. 1 additional modulo 5 of 4. And by the definition, 1 plus 4 is 5. 5 divides 5 is, remainder is, 5 divides 5 is 1. But remainder is 1 time cancelled. But remainder is 0. Okay. Now 5 is not repeated here because now those elements must be filled in the composition table in the only in the set of elements. Set of elements in between 0 to 4 is there. Okay. Now those elements in the given in the integers modulo 5. Okay. And in the same manner, 2 plus 0, 2. 2 plus 1 is 3. 2 plus 2 is 4. Okay. 4 less than 5. Okay. Now that is the result. 2 plus 3 is 5. 5 divides 5. Remainder is 0. That is A plus B minus n. A plus B is 2 plus 3, 5. 5 minus 5 is 0. Okay. Now by the definition, ORR 5 divides A plus B. 5 divides 2 plus 3. Remainder is 0. ORR, according to the your textbook, another condition is A plus B is greater than or equal to n. We are getting the value is A plus B minus n. So 1 plus 4 is 5. 5 minus 5 is 0. Now that is the result. So 1 plus 4. 5 is here. The result is 0. At the same time, 2 plus 3 is 5. 5 minus 5 is 0. Okay. 2 plus 3 minus 5. It is greater than or equal to n. Okay. That value is 0. Now 2 plus 4, 6. Okay. 6 divided by 5 means remainder is 1. In the same manner, 3 plus 0, 3. 3 plus 1 is 4. 3 plus 2 is 5. 5 divides 5 is remainder is 0. 3 plus 3 is 6. 6 divides 5. Remainder is 1. 6 divided by 5 or 5 divides 6. Whatever it is. The value is 1. Okay. By the definition, A plus B minus n. Here A plus B means 3 plus 3. 6 minus n means 5. 6 minus 5 is 1. Now that is also one of the giving the result. Okay. And in the same manner, 3 plus 4, 7 minus n. N means 5. 7 minus 5 is 2. Okay. Now, according to the composition table, all the entries must be filled in the composition table and not exceeding other side of the elements given in the other side of the elements of the set. Okay. Now, modulo 5 means set of 0, 1, 2, 3, 4 by definition of integers modulo n. That is Zn equal to set of 0, 1 to so on n minus 1. That's why here Z5 under addition modulo 5. This structure is read as Z5 comma plus 5. Means Z5 under addition modulo 5 to form a group because closer relation. Now in between we are taking in two elements. Now closer relation must be satisfied in the set of the element. Okay. Now in between the elements 4 plus 1 is 5. Suppose there are two elements. A element is 4, B element is 1. Okay, 4 addition modulo 5, 1. We are getting the value is 0. 0 is also given in the set. So that's why closure condition is satisfied. Because all the entries must be filled in the composition table automatically. Now finally we have to conclusion. we must conclude that Z5 under additional modulo 5, all the entries must be filled in the composition table, all the postulates were all the properties were all the laws were all the axioms, whatever it is, to form a group. Okay, and also if already you have to prove that a group Z5 is a group with respect to additional modulo 5 and commutative property is also satisfied, that is called an invariant group. Suppose 4 additional modulo 5 2, 4 plus 2 is 6, 6 minus 5 is 1, and at the same time 2 plus 4, 2 plus 4, 2 plus 4 is also 6, 6 minus 5 is 1. Now we are getting the result is 1 and getting the result is 1. So a apply a additional modulo 5, 2 equal to 2 additional modulo 5, 4. Now the commutative property is satisfied. That's why Z5 under additional modulo 5 is an invariant group when it is commutative property is satisfied. Okay. Now this is very important. Now given the set of the elements is finite, that is called a finite group. Okay. Now what is the finite and infinite groups? When the set of the elements, when the group of the elements must be a finite, that is called a finite group, and otherwise it is an infinite group. Okay. Now suppose set of 0, 1, 2, 3, 4, 5. Now that is the fixed elements. When the group of the elements must be a finite, means elements are finite. Elements are fixed. That is called a finite group. Otherwise it is an infinite group. Okay. Now in the same manner, multiplication modulo n is also defined. Now here the multiplication modulo n definition is just you have to see here. Okay. A additional modulo A multiplication modulo n of B equal to R. Okay. Here n be any integer, that integer is greater than 1. Very important concept. Okay. In the additional modulo 5, to form the above example, Z5 under additional modulo 5 is an infinite. Sorry, it is a finite invariant group because these elements are finite, fixed elements given in the set. That's why all the properties are satisfied. G1, G2, G3, G4, G5. Okay, all the properties are satisfied and all the entries must be closed in the composition table. That's why given this example to form a finite invariant group. Okay, see the next one. Here, this is the multiplication modulo n. How to define the multiplication modulo n? Here, A and B being any two integers. There are two elements given in the set. Here, n being a particularly integer that must be greater than 1. Now, here the multiplication modulo n defined of the form A multiplication modulo n of B equal to small r. Now, this is the meaning of R needs remainder. Okay. Here, n divides A into B. N divides AB, or AB is divided by n, whatever it is. The product of AB is divided by n. We are getting the remainder value is called, that is small r. Now that is the A under multiplication modulo n of B equal to small r. That is n divides A into B. Okay, we are getting the remainder. Now that is the final result. Now see this some other examples. 2 into 3 is 6. Okay, 2, 3, 6. 6 divided by 4. What is that? 6 divided by 4 means one time cancelled, the remainder is 2. That is the result. 2 lies between, what is the elements of the set? 4 means modulo 4 means multiplication modulo 4 means set of 0, 1, 2, 3. Okay, that's enough. The 0 is not here. Okay. 4 into 8, 32. 32 divided by 10. 3 times cancelled. 2 remainder. 5 into 6, 30. That is the product of 5 into 6, 30. 30 divided by 7. What is the result? 30 divided by 7 means 4 times cancelled. The remainder is 2. 3 into 6, 18. 18 divided by 9. Where 2 times cancelled, but remainder is 0. That is the multiplication modulo n. Multiplication modulo n means set of integers modulo 6. This is also one of the examples. Observe very carefully. This is one of the special binary operation. Multiplication modulo 6 is there. Set of 0, 1, 2, 3, 4, 5. Okay, that's enough. Okay. Now 0 inverse 0 into 0. 0 is multiplying with anyone. We are getting the values are 0. 1 multiplying with the 0. 0. 1 into 1, 1. 1 into 2, 2. 1 into 3, 3. 1 into 4 is 4. 1 into 5 is here. Okay. Now given the example must be referred. Now Z6 under multiplication modulo 6. Multiplication modulo 6 means set of 0, 1, 2, 3, 4, 5 because n minus 1 values. Okay. Now 2 multiplying with each and every one. This is the column and this is the row. Each multiplying with 0, that is why that values, those values are 0 is there. 1 into 1, 1, 2 into 1, 2, 3 into 1. Okay, same. Like same 1 into 2. This is 2 into 2 is 4. 2 into 3, 6. 6 divided by 6 means remainder is 0. Okay. 2 into 4, 8. 8 divides by 6. Remainder is 2. 2 into 5, 10. 10 divides by 6. One time cancel. One time is also cancelled. Remainder is 4. Now that is the multiplication of this part. Okay. Now all the entries must be filled. Suppose one of the example 4 multiplication modulo 6 of 2. 4 into 2 is 8. 8 divided by 6 means the result is 2 is there. Now that is the same manner. All the entries must be filled in the composition table. We have to form the composition table with respect to the rows and columns under multiplication modulo 6 of their elements. Okay, that's why Z6 under Z6 comma multiplication modulo 6. Now in term, now it is written as the set of integers modulo 6 with respect to multiplication modulo 6. With respect to multiplication under modulo 6 to form a finite, in sometimes to form a finite equivalent group, in sometimes to form a finite group is there. Okay, that's the answer. Now this is also a special binary operation, addition modulo 6 and multiplication modulo 6. Now another one is here 2.2.17, the set of non-zero integers modulo 5. Non-zero integers modulo 5 means non-zero means not equal to 0. Now what how to get the elements? Set of 1, 2, 3, 4, n minus 1, 5 minus 1 is 4. Not equal to 0 means non-zero, without the 0 of the elements 1, 2, 3, 4. We are taking given the set 1, 2, 3, 4 and here 1, 2, 3, 4. Here not equal to 0 means non-zero elements of the given the set. With respect to multiplication modulo 5 is a group. This is also one of the problem. First of all, you have to construct the composition table. The given set of elements must be arranged as the rows and this is the rows and this is the columns. 1 into 1 is 1, 1 into 2, 1 into 3. Now 1 is always multiplying with the given the set of elements. We are getting the same elements given in the set. Okay. 2 into 1 is 2. 2 into 2, 4. 4 is less than 5. We are getting the result 4. 2 into 3, 6. 6 minus 5. That is value is 1. Or 6 divides by 5. One time cancelled, remainder is 1. Now, any one is also explained here. Okay, any type of the explanation here. Now, 2 into 4, 8. 8 minus 5. Okay, 8 divided by 5. 8 divided one time is also there. Now, 3 into 4. Yeah, just see here. 2 into 4 is 8. 8 divided by 5. Okay. Now we are getting the result is 3 is there. Now this is the wrong entry. Just you have to listen carefully. Okay. This is 3. 3 into 1 is 3. 3 into 2 is 6. 6 divides by 5 means 1. Okay. 3 into 3, 9. 9 divided by 5. Remainder is 4. 3 into 4, 12. 12 divided by 5. 2 times cancelled. Remainder is 2. Okay. Students, please listen carefully. This is 3. Please note down. Not 2. Okay. Please, this is the correction. Okay. Next. 4 into 1 is 4. 4 into 2 is 8. 8 divides by 5. 8 divided by 5 means one time cancelled. Remainder is 3. 4 into 3, 12. 12 divided by 5. Remainder is 2. Only you must note down the remainder only. Okay. That is the definition. A multiplication modulo n of b equal to small r. R beats remainder. 4 into 4 is 16. 16 divided by 5. 3 times is cancelled. But remainder is 1 here. Now, this is the composition table. Just you have to observe all the entries must be filled in the composition table, given in the set. 1, 2, 3, 4. But not outside of the elements is not here. Suppose outside of the elements is here. Now that does not form a group. Okay? That's enough. If it is outside of the elements given in the composition table, now that is not a group because postulates are not satisfied here. Okay. Now in particularly just we observed that all the postulates, all the entries, okay, all the postulates, all the axioms, whatever it is, postulates, axioms, properties, laws, whatever it is. Now that is the meaning is it is same or conditions. Okay. Now closure law, associative law. Associative means we are taking any to 3 elements, 2, 3, 4. 2 into 3 is 6. 6 into 4 is 24. 24 by 5. What is that? 24 by 5 means 4 times cancelled. Remainder is 4 is there. Suppose step by step is there. 2 into 3, 6. 6 divides means 1. 1 into 4 is 4. 1 into 4. Just write here. 1 into 4 is 4. Okay. Now 3 into 4 is 12. Associative law. Associative law means we are taking any 3 elements. That is 3 into 4, 12. 12 divides 5 means remainder is 2. 2 into 2 is 4. 4 less than 5. Now that is the remainder. So associative law is satisfied. Here particularly just you have to observe here. One is the multiplicative identity under the ordinary composition, and in the same manner multiplication module n is the special binary operation. Here one is also one be the multiplicative identity. Okay, but it is less than 5 here. Okay, how to get the inverses? Just you have here. What is the multiplicative identity? Here one be the multiplicative identity. One is multiplying with every element that is the same element here. 1 into 2, 2. 1 into 3 is 3. 1 into 4 is 4. Or the same. 4 into 1 is 4. 3 into 1 is 3. 2 into 1 is 2. 1 into 1. So left identity, right identity must be equal. That is called an existence. Okay. Now here the existence of inverse is there. What is the existence of inverse? Listen carefully. Now one identity element is always represented as the 1 be the inverse is 1. 2. 2 how 2 which the value is coming at 1? 3. So because 2 into 3 is 1. So 1 be the multiplicative identity because inverse always must be it depends upon the identity. Now 2 which element is get the 1? 3. So 2 be the inverse is 3. 3 be the inverse is 2. That is we are coming the element is identity here. Okay, 3 multiplication modulo of 2 equals to 1. 2 multiplication modulo of 3 equals to 1. So this is that's enough. Now therefore 2 inverse is 3, 3 inverse is 2 because when it is coming the identity, now that element is called an inverse of the given element. Now 4 when it is given the 1, 4 divides 4. That is 16. Okay, 16 divided by 5 means we are getting the value is 1. So 4 inverse is 4, 3 inverse is 2, 2 inverse is 3, 1 inverse is 1. So inverses of 1, 2, 3, 4 or 1 is 1, 2 is 3, 3 is 2 and 4 is 4. Now that is the inverses of under multiplication modulo 5. Now according to the given the multiplication modulo integer, multiplication modulo 5. Now to form a finite group. Okay, that's it. Okay. Now already group is also defined and some concepts are there. Okay. Now yesterday, now this theorem is also explained here, cancellation laws, and just you have to see this theorem. Now this theorem is very, very important in the final examination. That theorem is prove that a finite semi-group cancellation laws holds in capital G. Okay. Do the cancellation laws, how to get the group corresponding to the finite semi-group. Okay, here just you have to write the given this part, given this data. First of all, S under multiplication is given to a finite semi-group. Finite means given the set of the elements must be a finite. Suppose n consisting of the elements given in the set. Now write as a finite set is capital S equal to set of. Now here A belongs to S, A be any one of the element. Now that element is A1, A2 and so on, AN. Now in between, suppose AI and AJ. But here the index elements are not equal here. I not equal to J. Just like that, 1 not equal to 2, 2 not equal to 3. In the same manner, I not equal to J, AI element, AJ element in between A1 and AN. So there are two elements that those elements are distinct and different. Okay. Now, first of all, now the given the data, let us be a finite semi-group. Finite means now given the set, we must assume that finite elements given in the set, and we are taking any two elements AI and AJ in between A1 and AN. Now those elements are not equal. Now that it must be distinct. Suppose one element is taken given in the set, AI element is also taken given in the set. Just you have to write the left side of the finite set. AI is also combining with the set of the each and every element to write as A1, A1, AI, A1, AI, A2. AI is also multiplying with each and every one. That is AI of S. AI, A1, AI, A2, so on, AI, AN. And at right side of the set is SAI. AI must be defined at right side from the given the set. SAI equal to A1 AI, A2 AI, so on, AN AI. Now, here any element given in the set is multiplying with each and every elements for the given in the set. Now that is left side and right side of this part, AIS and SAI. Now this theorem is very, very important. Please note that it is very clear. Okay, AI and AJ equals to, suppose here AJ, AK values, AI, AJ, AI, AK. So these two elements given in the set, AI, AJ and AI, AK. Now here these two elements are different and distinct. Here when it is left cancellation law, we have to apply the left cancellation law. AI is also cancelled. Now we are getting the result is AJ equals to AK. When J equals to K, we are getting the result is AJ equal to AK. Okay. Now in the left side of the set is AI, A1, AI, A2 and so on, AI, AN. These elements are distinct elements. These elements are distinct elements. Here N be the number. Suppose AI is also one of the subset of the given the set. What is the AIS? This is also one of the subset for the given the subset, capital S. For the set is capital S. And AIS and S both are have the same number of elements and distinct elements. Automatically AIS equal to S. Similarly, SAI, right side of the element for the given the set is also combining with the right side element. SAI is also equal to capital S. Finally, AIS and SAI both are equal to the given the set of the same number of elements. Automatically, AI means A, now AI means A. Therefore, AS equal to S, SA equal to S. For any element A belongs to S is there. In particular, suppose A be any one of the fixed element given in the set. Okay? Set means set of A1, A2, so on, AN. A be the fixed element. So therefore, A belongs to AS and hence A equal to AE. Because identity element is also there. What is identity? By G3 property, A into E, that is we are getting the same element that is A. Here E is also belongs to one of the element given in the set. That's why that is the common element to fix. Now common element is XB, one of the element given in the set. First of all, we shall prove that XE equal to X is there. Because identity element is also here. XE equal to X. Here X belongs to S and X is also same, S equal to SA. Now automatically from the subset, SA is also subset of S. Therefore same number of elements given in the set S and SA. Therefore same element is also repeated in the SA. Suppose X equal to, here any element Y belongs to S, X equal to YA according to this one. X equals to YA. For some, Y belongs to S is there. Now, here just we have to observe here, X into E equal to, what is the value of X? Here, X equal to YA is there. With respect to the SA set. Now, Y, that value is substituting X, replacing by X equal to YA of E. Now, we have to write the associative law, Y of AE. Y of AE is also down by G3 property, this value is A. Now Y into A is equals to X is there. Y into A equals to X. Now this is the, according to this one, YA value is the X is here. Now then XE equal to X for all X belongs to S is there. Similarly, there exists that any one of the function F belongs to S is such that F into X equal to X. into x equal to x. For all x belongs to s is there. Now we have f equal to f into e. F into e means e is there. X into e equal to e into x equals to x. By G3 property, here x belongs to s and e beats identity element in s. Now every element of s, now given in the set, when it is form a group, when we will form a group, automatically the given set of the elements, every element must be expressed the inversible, part. Okay, here a belongs to s. Suppose a belongs to s is there. A into s equal to sa. Automatically, then the above mentioned here, this proof is also clearly, it is very clear. A into s equal to s into a equal to s is there. Suppose any identity element in SA or AS. Then exists, there are two different elements x and y. Those elements are belongs to given in the set. E can be expressed as x into a. Now that is also in the same manner e equals to. Finally, x equal to xe, x of replace e by ay. Now, by associativity, xa of y. Xa means identity. E into y equals to y is there. Finally, we are getting the result is a into x or x into a. Then it is e is there. Identity element is there. Therefore, what is the inverse? X be its inverse of a is there. Inverse element. How to explain the inverse element? When the given the elements of the set, when it is identity, now that element is called an inverse. Here x be the multiplicative inverse of a in capital S. Therefore, by G4 property, a b equal to ba equal to identity is there. Here b by x, you have to mention the b by x is there. A b equal to ba equal to a by G4 property. Therefore, x is the inverse of a in S. Therefore, finite semi-group cancellation laws, when the left and right cancellation law must be hold. Therefore, given the finite subset, finite semi-group is a group. Okay, that's enough. This theorem is very important. It is noted down. Okay. Now, these theorems are explained here. That is 2.2.9. That is, and in a group capital G, the identity element is unique. That is the theorem. That proof is 2.2.9. And 2.2.10 is in a group capital G, an inverse element is unique. That is the uniqueness of inverse theorem. That is 2.2.10. Now that is the cancellation laws. Already we have explained here. Okay. Now this theorem is there. Just see here this theorem. Please stand the line. Please stand the line. Please stand the line. Classroom.
2.3.5, sir.
Here because here there is no supply. Okay. Now to a hotspot you have I explained here. Okay. Please stand the line. Please. Side apps are also okay. Okay, just try to see here. Problem is here. Okay, any doubts, students? No? Okay, here 2.3.5 students. Okay, just you have to see this one. Let G under multiplication be a group and A comma B belongs to G. Now this is one of the theorem, very most important theorem. G under multiplication be a group and here A comma B belongs to G. Here the given the results are true. Okay. Now first one AB equal to E. When now this is also first condition. Corresponding to the first condition is AB equal to A. This is the referred as by G4 condition. Here B is the inverse of A. Now if it is AB equal to E by G4 condition applying, what is the value of P? That value is A inverse. That is the necessary and sufficient part is also satisfied here. And next property is, that is the simple property. A inverse whole inverse equal to A. And the fourth one is AB whole inverse equal to B inverse A inverse. These three properties are, these three results are true. Okay. When it is here G under multiplication be a group and here A comma B belongs to capital G. Okay. Suppose here the first condition is just you have to see here the first condition. Anyone is explained? Anybody is explained here? First one. First one. Whatever it is. Oh. Anyone explain? Nobody? Okay, just you have to see here. What is the first one? AB equal to E means B can also be written as E into B is there. Okay. What is the value of B? B equals to EB. Okay. What is the value of E? By G4 condition, E means A inverse A of B. Now, by write the associative part, A inverse of AB. A inverse of AB is there. Now, what is the value of AB? AB equals to E is there. That is the given part. Now, substituting given this one, A inverse into E. Finally, identity element is multiplying with any one. We are getting the value is A inverse. Now, right. Finally, we are getting the value B equal to A inverse. That is the first one. Now, second one is here. B equal to A inverse. So, we are taking the B equal to A inverse. This is the next part is also satisfied. Now, that the substituent part B equal to A inverse implies multiplying with that left side A. AB equal to AA inverse. What is the AA inverse? By G4, AA inverse is identity. Now, we are getting the value AB equal to E is there. Similarly, A inverse into A means identity. Identity can be also written as E into A. So, what is the value of E into A? That value is A. Now, here the value is A means A inverse whole inverse by first condition. Okay, by first condition, we write just you have to write the A inverse equal to here A inverse equal to A inverse into A means identity. Therefore, here E into A equal to means A inverse whole inverse because A can also be just how to by first condition. What is the first condition? A B equal to E. B equal to A can be A converting into this side. The value is A inverse. Okay. Now substituting this value from the first condition A into A inverse equal to identity. What is the value of P? A inverse. Okay. Now that is A inverse whole inverse. Now by the first condition substituting P equal to A inverse in the first condition we are getting the result is 2 is there. And the third condition is here. AB whole inverse means by first condition again replacing A by AB. Okay. Now AB of B inverse A inverse, because A value is AB. Okay. And B value is B inverse A inverse. AB of B inverse A inverse, write the associative part AB of B inverse A inverse. Again, this is also associative A of BB inverse. BB inverse means identity. Therefore, A into E of A inverse. A inverse equals to identity. By first condition, this value is A and this value is A inverse. A into A inverse equal to identity from the by G4 condition. And according to that, here B inverse A inverse is the inverse of AB. That is the concept. It is very simple. Okay. What is the idempotent element? Okay. It's very important. Idempotent means that G under multiplication be a group in any element of the group is there. Suppose A be any one of the element. A belongs to capital G. A into A equal to A. Here A is called idempotent element. When this condition must be satisfied. Okay. A into A equal to A. Here A is called idempotent by this condition. Therefore, that's why here A is called idempotent element. Therefore, A is an idempotent in G under multiplication. A into A equal to A if and only if A into A equal to A can also be written as A into E by G3 property. Therefore, cancellation law, left cancellation law by A equals to E is there. Okay. Therefore, finally, suppose in the group of the element is A belongs to G. If it is that element is idempotent, it means we are getting the result is A equal to E is there. That is the idempotent definition. Please note down. Now, what is the identity element? Which is the idempotent element in the following answers? Identity, which is the following true? A into A equal to A into B equal to A. Okay, A into E equal to A into A, E equal to E. Now there are four answers here. Now this is the idempotent concept. A into A equal to A is there. When it is applying given in this session, because A can also be written as, because A be the one of the element of a group, A by G3 condition, A can also be written as A into A. Now we are getting the result is when the left cancellation applied, A equal to E is here. Okay, if it is idempotent element of this part, A be the idempotent element. What is the result? A equal to E is the result. Okay, that's enough. There are direct product. Okay, now here the direct product means there are two groups are there. G1, G2 be any two groups. That groups of the Cartesian product here cross with the one of the relation G1 cross G2 or G1 into G2, whatever it is. Here, capital G equal to G1 into G2 means this is the direct product of the group. Okay. Suppose here in G1, in the regular ordered pair, because this is the ordered pair relation. Here A1, B1 is one of the relation, A2, B2 is also another relation. Now, in the direct product, we are getting the result is A1, A2 into B1, B2. Means A1, B1 and A2, B2 is there. Okay, here even E2 is the identity element in the direct product concept. Okay, now there are so many worked out exercises here. Now this is very important concept. Please listen carefully. Let X be any non-empty set. Okay, now that is the bijection part. Already you have to explain in yesterday. Okay, M of X under circle be a monoid through the inversible condition. Suppose X be any non-empty set. M of X be the set of all mappings. Set of all mappings of capital X into, what is that? 20. Yeah. Just you have to hear. X into X. F maps X to X be a mapping. Yesterday I have explained here this theorem. What is that? Here F is a bijection. First of all, F is a bijection. Bijection means injective and bijective mapping. Now, when it is injective and bijective mapping, you have to take care. Automatically, given the function is inversible in the monoid concept. Monoid concept means M of X under circle. Circle be the binary composition of a mapping. Now, this theorem is also very important. Yesterday explained here. Now, just you have to, once I have to repeat here, F maps X to X is a bijection map. Then automatically any element, for each element, Y belongs to capital X, that is the unique element, means X belongs to X is the unique element. What about the relation X and Y of the functional relation? F of X equal to Y. Now here, X being the, what is the meaning of X? This is the F inverse of Y. Therefore, f inverse of y equal to x from the concept is y equals to f of x. What is the inverse condition through the functional map? F circle f inverse equal to f inverse circle f equal to identity map is denoted by capital I. Therefore, when the closure, associativity, identity, these three are satisfied, that is called a monoid. Then it's why. When the monoid concept is also given. Now, given the function is monoid. Now, only inverse condition must be satisfied. That is called a group. And the inverse condition is f inverse is denoted by G. Therefore, f circle G equal to G circle f equal to I is here. That value since G equal to f inverse. Therefore, f circle G with respect to y means f of G of y. Now, that can also be written as f circle G of y. F circle G means I. Identity of y equal to y is there. Therefore, given this one, according to given the relation, this is the subjection part. Okay, from f of x equal to y, x equal to f inverse of y. Okay, replacing x by f inverse y, f of f inverse of y equal to f inverse of y equal to y. So that's why given the function is bijection. Okay, students, this example is very important from the monoid concept. What is the monoid? M of x and circle be a monoid. Now we have to circle be the one of the binary operation. Then it have form a then to prove that in the monoid circle as the composition, there are so many functions given in the monoid set of the monoid. Therefore, irreversible condition must be satisfied. Then automatically, when it is a bijective mapping, now then it form a group is there. Okay. Now this problem is very important, and this type of problems, there are so many problems repeated here. One of the problem, students listen carefully. This problem is very important in the final examination. Okay. Study. Now just you have to see here. Let Q plus be the set of all positive rational numbers. Okay. Q plus be any one of the set. That set being a positive rational numbers of the positive rational numbers is available given in the set. And we define a binary relation. What is the binary relation? Star be the one of the binary operation on Q plus set. So star be the relation. Suppose in Q plus A and B be any two elements belongs to Q plus. So star be the binary operation. So what is the close relation? A star B equal to AB by 2. That is the given part. Now here Q plus under star is an invariant group. Now very important. Okay. Now Q plus under star is an invariant group. Okay. First of all, so we have to mention the given the data. Star is a one of the binary operation on Q plus. Here A comma B belongs to Q plus. AB is also belongs to Q plus. What is the Q plus means Q being the rational number. Now given the relation is the rational part, P by Q form is there. Okay, that's there is no doubt. 2 not equal to 0. When the AB belongs to Q plus, AB by 2 is also belongs to Q plus. Q plus means a positive rational number. Here A and B both are positive rational numbers. Now that is the closure condition is verified because AB by 2 means A star B. It also belongs to Q plus under star. Now we are taking any three elements. Okay. Now how to derive the invariant group? According to the Q plus with respect to the composition is an invariant group. Means first of all closure condition is also given. Now according to the condition, AB belongs to Q plus and AB by 2 belongs to Q plus, and finally AB by 2 means given part is that is the defined part is A star B. Therefore Q plus under star is closed. Second one, associative. Associative means we are taking any three elements given in the set. Now these are all assumptions. Just we have to create Q plus B one of the set, positive rational number set. A, B, C or any three elements given in the set. A star of B star C equal to A star of B star of C means BC by 2. Suppose BC by 2 means from the relation A star B equal to AB by 2, B star C equal to BC by 2. Now A star of BC by 2 means BC by 2 element is Y. A star Y means AY by 2. Okay, Y is also substituting value. A into Y means BC by 2. Now ABC by 4 is there. ABC by 4 can also be written as AB by 2 star C. AB by 2 means A star B of star C. Therefore, star is associative. Okay. Now it is very clear. Okay. Next one. In Q plus, what is the identity part? Existence of identity means A star E equal to E star A equal to A. That is the by G3 property. But how to? Just you have to see here again. A star E equal to A. Suppose A star E equal to A. A star E means by the definition AE by 2 equal to A. AE by 2 equal to A. If both sides A cancel, now E value is 2. E value is 2 because A star E means AE by 2. Now this is the not correct proposition. Okay, this is not correct way. By G3, first of all, you have to write that by G3. A star E equal to E star A equal to A. Suppose right identity is A star E equal to A. A star E means by definition AE by 2 equal to A. A cancel. What is the value of E? E equal to 2. When A star B equal to EB by 2, identity element is 2 by G3 property. Okay, identity element is 2. Suppose A star B equal to AB by 3. What is the identity element? That is 3. A star B equal to AB by 4. What is the identity element? E equal to 4. By G3 means A star E equal to E star A equal to A. Therefore, AE by 4 equal to A, E equal to 4, when A star B equal to AB by 4. Okay. Now, here the by condition, identity element is 2 is there. Next, last one. Here, A belongs to Q plus. A star B by G4 property. A star B equal to B star A equal to E is there. What is the A star B? AB by 2 equal to E. AB by 2 equal to E means 2. AB equal to 4. What is the value of B? B equal to 4 by A. Therefore, 4 by A is the inverse of A belongs to Q plus. Now, when AB by A star B equal to AB by 2, what is the inverse? 4 by A is the inverse of small a in Q plus. Suppose A star B equal to AB by 3, B equal to 9 by A. A star B equal to AB by 4. What is the inverse value? B value is 16 by A. Okay. A star B equal to AB by N. Okay. What is the inverse? B equal to N square by A. Okay. That's it. Therefore, automatically by G4 condition, A star B equal to AB by 2. That value is an equivalent to identity element. That value is 2. Therefore, B equals to 4 by A. That is the inverse of A. Finally, Q plus under star to form a group is there. Q plus under star to form a group is there. Finally, A star B equal to AB by 2. AB can also be written as BA. BA by 2 means B star A from the definition of this part. When A and B both elements are positive rational numbers, finally Q plus under star is an abelian group. Okay. Now this is clear part. One by one. First closure, second one associativity, third one existence of identity, fourth one existence of inverse. Automatically we are easily to get. There are so many problems are practiced when A star B equal to AB by 3 to form a finite abelian, to form an abelian group. AB by 4 to form an abelian group. Okay, A star B is not particularly mentioned here. Simply circle is also there. A circle B equal to AB by 3 is there. Okay, Q plus under circle to form an abelian group. Okay, there are so many problems practiced here. Suppose AB by 5. Well, now identity element is 5. B equal to 25 by A. That is the inverse of A. Okay. Now all the axioms are satisfied, including and after that form a group formation. Q plus under star is also satisfied the commutative property. Finally, Q plus under star is an abelian group. That's it. Now, students, just you have to see here. Now these problems are also seen here. Tomorrow we will explain here, and last 4 classes. Tomorrow class is also subgroups and some other problems are also practiced here. Okay, and tomorrow we will begin with the subgroup concept and some other theorems are also there. Because okay, now just you have to see and once you have to repeat a number of times and see this session. Number of times are also just have to watch and easily to understand the subject concept. Okay. Now thank you one and all. Now already time is over. This is 11:40. Okay. Any doubts? Now if you have any doubts, please contact with my mobile number now or through the WhatsApp part. Okay. Today just I have posted some other important concept in the final examination in WhatsApp group. Okay. Thank you, one and all students. Any doubts? Any doubts? Students are staying here. Okay. Thank you, one and all. Wish you all the best.
Thank you, sir.
Most welcome.